The objective of this presentation is to gain fundamental insights into the mixture permeation characteristics of microporous membranes. Specifically, we underscore the importance of using the spreading pressure concept to describe mixture permeation across microporous membranes constructed, say, of layers of DDR zeolite, ZIF-8, or chabazite. Let's see how a microporous membrane is constructed. Take the example of ZIF-8. It consists of cages of 13 angstrom in diameter, and each cage is separated from adjacent cages by narrow 3.3 angstrom windows. These windows are flexible, and this flexibility allows molecules that are slightly larger than 3.3 angstrom to pass through these windows. Typically, the membrane would be constructed of thin layers of about 50 microns on a support, which is a macroporous. In this case, say a titanium support. And ZIF-8 is a good choice for separation of mixtures of, say, carbon dioxide, methane, carbon dioxide, hydrogen, methane, hydrogen. And the important advantage of ZIF-8 for CO2 methane separation is both adsorption and diffusion complement each other, leading to high permeation selectivities in favor of carbon dioxide. The company called NGK Insulators in Japan offer membrane modules which have a monolithic structure, and the inner walls of the tubes are coated with a thin layer, typically about 20 micrometers in size, this layer. And this layer consists of DDR zeolite that allows selective CO2 permeation from a CO2 methane mixture. Another important choice for use as thin microporous layers in membrane constructs for mixture separation is a chabazite zeolite. One unit cell of chabazite consists of 6 cages. The volume of one chabazite cage is slightly larger than a single cage of DDR zeolite, but significantly lower than a single cage of ZIF-8. The cages are separated by 8-ring windows, and the window dimensions are about 3.8 angstrom in this direction and 4.2 angstrom in this direction. In the following slides, we examine and analyze the characteristics of permeation of a variety of mixtures across a SAPO34 membrane. SAPO34 has the same structural topology as chabazite zeolite. The data on the mixture permeation characteristics and the analysis of the data are available in the publications listed here. Let's first examine permeation of mixtures of methane and hydrogen across a Chabasite membrane. This cartoon shows the relative dimensions of methane and hydrogen. Hydrogen is a much smaller molecule and can hop from one cage of Chabasite to the adjoining cage through the narrow windows much more quickly than in methane. Let's have a look at the animations created from MD simulations of intercage hopping of methane, shown here in blue, and hydrogen shown in white. Hydrogen is observed to undergo intercage hopping much more frequently than its partner methane. Methane has a higher adsorption strength than hydrogen, but hydrogen has a far greater mobility. And the mixture permeation characteristic is described by a combination of diffusion and adsorption. The adsorption selectivity favors methane, but the diffusion selectivity is significantly higher in favor of hydrogen. The experimental data on the component permeances are plotted here in this graph as a function of the upstream partial pressure of the components. The component permeance is described as the flux divided by the driving force, and the driving force is the difference in the partial pressures of fugacities in the upstream compartment and in the downstream compartment. The filled symbols are the permeation characteristics for the mixture, and the open symbols are the permeation characteristics of the single components. So let's look at hydrogen. The unary permeance of hydrogen is significantly larger than the unary permeance of methane. However, the permeance of hydrogen in the mixture is significantly lowered, and this lowering is due to the fact that the adsorption selectivity favors methane. But taken as a whole, the diffusion selectivity that favors hydrogen overrides the adsorption selectivity favoring methane, and the mixture permeation is in favor of hydrogen. Let's examine permeation of mixtures of carbon dioxide and methane across a Chabasite membrane. CO2 is a pencil-like molecule, and the cross-sectional dimension is significantly lower than a methane molecule. And the diffusivity of CO2 in Chabasite is significantly higher than the diffusivity of methane because CO2 can jump lengthwise from one cage to the adjacent cage as observed here. Methane, on the other hand, is more severely limited in its intercage hopping because of its larger cross-sectional dimension. Now CO2, because it possesses a quadrupole moment, also has a higher adsorption strength than methane. Both diffusion and adsorption favor the permeation of CO2 across a Chabasite membrane. The experimental data for mixture permeation across a SAPO34 membrane, which has the topology of Chabasite, is shown here, in which the component permeances are plotted against the upstream partial pressures. The fill symbols are the component permeances in the mixture, and the open symbols are the component permeances of the single components. We note that for CO2, the permeance of CO2 in the mixture is practically the same as for the single component. Whereas for methane, the permeance in the mixture is significantly lower than the permeance of the single component. This is because methane not only has a lower diffusivity than CO2, but it also has a lower adsorption strength. Both adsorption and diffusion favor CO2, and therefore the CO2 methane membrane permeation selectivity is significantly in favor of CO2. The permeation of mixtures of carbon dioxide and hydrogen across a Chabasite membrane is different from the two examples considered in the previous two slides. Hydrogen is a much smaller molecule and undergoes intercage hopping much more frequently than carbon dioxide, as is evident in the animations shown here that are constructed on the basis of molecular dynamic simulations. The white spheres, hydrogen, very mobile, is able to jump from one cage to the adjacent cage much more easily than carbon dioxide. Carbon dioxide, on the other hand, has a significantly higher adsorption strength than hydrogen. And the mixture permeation is dictated by a combination of adsorption selectivity and diffusion selectivity. The diffusion selectivity is in favor of hydrogen. The adsorption selectivity is in favor of carbon dioxide. The adsorption selectivity in this case overrides the diffusion selectivity and the mixture permeation favors CO2. This is evident in the experimental data in which the component permeances are plotted against the upstream partial pressures. The fill symbols are the permeances in the mixture, and the open symbols are the component permeances for the pure components. For hydrogen, the unary permeance is significantly higher than the permeance of hydrogen in the mixture, because hydrogen loses out because of its significantly lower adsorption strength. On the other hand, CO2 is much more strongly adsorbed, and the permeance of CO2 in the mixture is practically the same as the permeance of CO2 on its own. The net result is that mixture permeation is strongly in favor of CO2. This figure summarizes the experimental data on the component permeances of carbon dioxide, methane, nitrogen, and hydrogen. In each case, the unary permeances indicated by the open symbols are compared with the corresponding component permeances in mixtures. For example, the component permeance of CO2 on its own is compared with the component permeance of CO2 in mixtures with methane, red circles, hydrogen, yellow diamonds, mixtures with nitrogen, blue triangles, and in mixtures with methane and nitrogen, crosses. We note that for carbon dioxide, the component permeance of carbon dioxide in any mixture, whether it's a binary mixture or a ternary mixture, is almost the same, not quite exactly so, but almost the same as the unary permeance of CO2. But that is not the case for the component permeance of methane, nitrogen, and hydrogen. For nitrogen and hydrogen, for example, the component permeances for unary systems are significantly higher than the component permeances in mixtures. For methane, the component permeances of methane is higher than in mixtures with carbon dioxide and in a ternary mixture of carbon dioxide and nitrogen. But in a binary mixture of methane and nitrogen, the component permeances of methane are practically the same. So based on the information presented here and analyzed in this publication, I might add, one might be tempted to conclude that perhaps it's possible to compare or predict the component permeance of carbon dioxide in a mixture, because it's almost exactly the same as the unary component permeances. But it's not possible to predict the component permeances of methane, nitrogen, and hydrogen, because in mixtures they're significantly lower than the unary permeances. However, I would like to demonstrate in the following slides that this conclusion is rather pessimistic, and that if we adopt a fundamental approach to describing mixture permeation, then it is possible to have a good estimation of component permeances in mixtures using only information on the unary permeances. In developing our fundamental approach to describing mixture permeation across microporous membranes, we introduced three parameters: pi, phi, and theta. Pi is the spreading pressure introduced by the great thermodynamicist Josiah Willard Gibbs. The ideal adsorbed solution theory allows calculation of pi and its proxy phi that can be termed the surface potential. We shall demonstrate using Monte Carlo simulations of mixture adsorption that the adsorption selectivity is uniquely related to phi. The occupancy of guest molecules inside the pores, theta, is relatable to the surface potential phi. The intracrystalline diffusivities and diffusion selectivities depend on the surface potential phi that can be considered as a proxy for the pore occupancy. The membrane permeabilities and the permeation selectivities are uniquely dependent on phi. That is what we shall demonstrate in the forthcoming slides. All the background theories to our approach are described in detail in these publications that you may refer to. The description of the thermodynamics of mixture adsorption begins with the Gibbs adsorption equation, written in this form: A differential of pi equals the sum of the product of the molar loading of component I times the differential of the chemical potential of component I. A is the specific surface area, and pi is the spreading pressure within the units of newtons per meter. At thermodynamic equilibrium, the differential of the chemical potential of component I is related to the differential of the partial fugacity in the bulk of fluid phase by this expression. In the ideal adsorbed solution theory of Myers and Prausnitz, the partial fugacity of component I in the bulk fluid phase is related to the mole fraction of component I in the adsorbed phase by an expression that is the analog of the Raoult's law for vapor-liquid equilibrium. Pi superscript 0 represents the sorption pressure of species I, and the sorption pressures satisfy this expression that implies that the sorption pressures are such that the spreading pressure for mixture adsorption equals the spreading pressure of component 1 on its own and the spreading pressure of component 2. In these integrals, these represent the unary isotherms for component 1 and the unary isotherm for component 2. Since the surface area A is not easily accessible, it is convenient to define the surface potential phi as the spreading pressure times the specific area divided by RT. The surface potential can be determined from information on the unary isotherms. For the special case in which the unary isotherms are described by the Langmuir isotherms with saturation capacities Q1 sat for component 1 and Q2 sat for component 2, the integrals in the previous slide may be determined analytically to obtain phi in the following form. We also have the relation between the mole fraction in the adsorbed phase with the sorption pressures for component 1, the mole fraction of 2 in the adsorbed phase, which is equal to 1 minus x1, is related to the sorption pressure for component 2. Inserting these into the expression for the surface potential, we obtain the following relationship. Now, for a given set of partial fugacities of components 1 and 2 in the bulk fluid phase, and from information on the unary isotherm data fit, we know B1 and Q1 sat, B2 and Q2 sat. We can determine the mole fraction of component 1 in the adsorbed phase by solving this nonlinear equation. This cannot be solved analytically except for the special case where Q1 sat equals Q2 sat. In that case, the solution to this expression corresponds precisely with the binary Langmuir model. For the general case where the saturation capacities are unequal, we need to obtain the solution to this nonlinear equation by use of a root finder. And after solving this equation for the mole fraction x1, we can determine the sorption pressures by use of these expressions here. There's a further point to be made regarding the adsorption selectivity. The adsorption selectivity is defined as the ratio of the molar loadings to the ratio of the partial fugacities in the bulk fluid phase. And this expression may be rewritten in terms of the mole fractions, x1 and x2. And in view of this expression relating the partial fugacities and sorption pressures and mole fractions, we write the adsorption selectivity of 1 with respect to 2 as the ratio of the sorption pressure of 2 with respect to the sorption pressure of 1. Now, for the thermodynamic equilibrium to hold, the sorption pressures P10 and P20 yield the same value of the surface potential, and therefore these expressions imply that the adsorption selectivity is uniquely determined by the surface potential irrespective of the compositions in the bulk fluid phase mixture. We shall test this conclusion using CBMC simulations of mixture adsorption equilibrium. In order to test the conclusion reached in the previous slide, that the adsorption selectivity is uniquely related to the surface potential, we carried out configurational-bias Monte Carlo simulations for a variety of mixtures. The yellow diamonds represent 50-50 CO2-CH4 mixtures. The red circles represent 20-80 CO2-CH4 mixtures. The blue triangles represent mixtures of CO2 and methane in which the total fugacity is held constant at 1 megapascal, and the composition of the mixture is varied from 0 mole fraction CO2 to a mole fraction of unity for CO2. The crosses represent ternary mixtures of CO2, methane, and nitrogen in the proportion 20-40-40. The pluses represent ternary mixtures of CO2, methane, and hydrogen in the proportion 10-20-70. And the cyan-colored hexagons represent data for a quaternary mixture of CO2, CH4, nitrogen, and hydrogen. The y-axis is the adsorption selectivity of CO2 with respect to CH4 in all these mixtures. And we see that the adsorption selectivity is uniquely related to the surface potential phi as plotted on the x-axis. Precisely, this is the dependence that is predicted by the IAST. The dashed lines represent calculations of the IAST theory using data on the unary isotherms. So the adsorption selectivity of CO2 with respect to methane in a variety of mixtures can be predicted on the basis of data on the unary isotherms. The same conclusion regarding the uniqueness of the dependence of the adsorption selectivity on phi holds for CO2 nitrogen mixtures, CO2 hydrogen mixtures, mixtures of methane and nitrogen, mixtures of methane and hydrogen, and all this data is available in this publication. Molecular dynamic simulations of intracrystalline diffusivities show that the Self-diffusivities are uniquely related to the surface potential, and the diffusion selectivities, defined as the ratio of the self-diffusivity of component I with respect to component J, are also uniquely related to the surface potential. As illustration, let's consider the diffusion selectivity of hydrogen with respect to CO2. The MD data for binary and ternary mixtures are plotted here as a function of the surface potential. The red circles show the MD data for the binary mixtures of CO2 and hydrogen. The pluses represent the corresponding diffusion selectivity in a ternary mixture consisting of CO2, methane, and hydrogen. And the stars represent data for hydrogen CO2 diffusion selectivities in a ternary mixture consisting of CO2, nitrogen, and hydrogen. In all three cases, the diffusion selectivity of hydrogen with respect to CO2 is uniquely related to the surface potential. The same conclusion holds for diffusion selectivity of CO2 with respect to methane, CO2 with respect to nitrogen, CO2 with respect to hydrogen, as shown in this slide, and methane with respect to hydrogen, methane with respect to nitrogen. All this information is summarized in this publication. Let's turn our attention to permeation selectivities. The permeation selectivity of I with respect to component J is defined as the ratio of the permeability of component I with respect to the permeability of component J. If we carry out the derivation for the permeation selectivity, we note that the permeation selectivity is a product of the adsorption selectivity and the diffusion selectivity. We have already established that the adsorption selectivity is uniquely related to phi. And in the foregoing slide, we have established that the diffusion selectivity is uniquely determined by phi. Consequently, we should anticipate that the permeation selectivity is also uniquely related to the surface potential. This is indeed the case, as illustrated in this example for CO2 hydrogen permeation selectivity in Chambersite. Combining the data on the adsorption and diffusion selectivities, we can determine the permeation selectivities, and we note that the permeation selectivity of CO2 with respect to hydrogen in a binary mixture, indicated by these red circles, is the same as the value in a ternary mixture of CO2, methane, and hydrogen, indicated by pluses, and is also close in magnitude to the values in a ternary mixture of CO2, nitrogen, and hydrogen, indicated by the stars here. So compared at the same value of the surface potential, the CO2 hydrogen permeation selectivity in a binary mixture is relatable to the CO2 hydrogen permeation selectivity in ternary mixtures. Therefore, the key conclusion is that you can predict the characteristics of permeation in binary and ternary mixtures using information on unary systems. We carried out a comprehensive set of molecular simulations of adsorption and diffusion of unary systems, binary systems, and ternary systems of gas molecules consisting of carbon dioxide, methane, nitrogen, and hydrogen in Chabasite zeolite at 300 degree K. Based on this set of data, the component permeabilities of carbon dioxide, methane, nitrogen, and hydrogen are plotted against the surface potential. The open symbols represent the unary permeabilities, and the filled symbols are permeabilities in binary mixtures and ternary mixtures. We note that in almost all cases, the component permeabilities in a mixture has practically the same value as the unary component permeability, provided we make the comparison at the same surface potential. This holds for CO2, methane, and nitrogen. For hydrogen, we see that the unary permeability of hydrogen is slightly higher than the values in the mixture. But as a good approximation, we can predict the permeability of hydrogen in a mixture using data on the unary permeabilities. The key is to make the comparison on the basis of the surface potential that can be calculated from the ideal adsorbed solution theory. Let us see if this conclusion, based on molecular simulations, can be verified using the experimental data that is available for SAPO34 membrane, that is the structural analog of Chabasite zeolite. The experimental data on the component permeances of CO2, methane, nitrogen, and hydrogen are plotted against the surface potential in this figure. The unary permeances are indicated by the open symbols, and the filled symbols are the corresponding component permeances in either binary mixtures or in ternary mixtures. For all four guessed components, we see that the permeances in the mixture, be it binary or ternary, has nearly the same value as the unary permeance. This is an important conclusion because it opens up the possibility of predicting the mixture permeation characteristics based on data on the unary permeances. The important point, of course, is to make the comparisons not on the basis of the partial pressures at the upstream face of the membrane, but at the same surface potential at conditions corresponding to the upstream compartment in membrane permeation studies. This conclusion, which we draw for SAPO34 membrane, which is a structural analog of Chabasite, also holds true for DDR membranes, and should also hold for ZIF-8 membranes. The experimental data for component permeances of CO2 methane mixtures in DDR membrane are shown in this figure. We note that the component permeances in the mixture is practically the same as that for the unary systems, provided the comparison is made at the same surface potential. The same is true for mixtures of nitrogen and methane. The component permeance of nitrogen in the mixture, indicated by the blue triangles, is the same as the unary permeance of nitrogen, and the component permeance for methane in the mixture, is shown by the green squares, is this practically the same as the unary permeance of methane, provided the comparison is made at the same surface potential. The data presented here are taken from these publications. The component permeances of propene and propane in a ZIF-8 membrane are plotted in this figure. The permeances in the mixture, indicated by the fill symbols, are the same practically as the unary permeances compared at the same surface potential. In other words, you can predict the mixture permeation characteristics based on the characteristics of the corresponding unary systems. This conclusion is of significant importance in the development of microporous membranes for mixture separations.